So in the original situation, right, the volume is, we don't know, but it's the same volume throughout these things, right? Because the mass of the tank, or the volume of the tank is not going to change a lot. It's going to thermally expand just a little bit, but not really very much, right? Okay. Its original pressure is well, you got to use the real pressure. So not just how much more than an atmosphere it is, but what it really is, right? So we have to add 14.7, right? 1974.7. That was a good year, you know. Okay. 1974.7 psi. So that's the real pressure. 20 degrees Celsius. The real temperature is 293.15 kelvins, yeah? 20 plus 273, yes? Isn't that right? Okay. And then the real mass of the stuff, is the 23.6. I'm going to say N in parentheses because it's really not the moles, but it's just how much stuff we have. That's what N means, right? The N is going to be 23.6 minus 6.5, right? So what is that? That is 17.1, right? And now we can set up a thing here. Our volume is, we don't know. It's the same volume. Our pressure is what we want to find out, right? Okay. Our temperature is the same temperature, isn't it? The same temperature for the second part, right? So we can either put the same number in for it, right? Or we can just let it cancel, right? Okay. But now our N is different. Isn't our N different? Our N is different. It's 19.9 kilograms. So our N, right, is 19.9 minus 6.5, because you have to take away the steel tank to get just the mass of the gas, right? So this is 13.4, is it? Yeah. Right? And now we can set up, we can go from this situation to this situation by saying PV over NT is PV over NT, right? So the pressure is 1974.7 times V, right, over 17.1 times T, right, is P times V over 13.4. Haven't you just set up a really simple proportion? It's like that pressure is to that mass as that pressure is to this mass. Aren't they just proportional to each other, right? In fact, if you saw that as a student, I would have solved it this way. I would have just said 1974.7 times. It's got to be, if you have less stuff, you have less pressure, don't you? So it doesn't have to be the ratio 13.4 over 17.1. Yeah? Doesn't that make sense? If you have less stuff, you have less pressure, right? Half the stuff, half the pressure. You have half the collisions between the gas and the wall because you have half the stuff, yeah? So we can cancel, obviously these guys cancel. If you solve this for P, you end up with this expression, don't you? Right? I'm just challenging you to come up with that expression first from your understanding of, right? Okay. Now with that in mind, in the third situation, right? In this situation, we can set up something. Can't we do the same thing? We can say 1974.7. What is our volume is we don't know. Pressure is we don't know. N is still the same N, right? N is 13.4 kilograms because we're still talking about the 19, right? But the temperature now is what in the third situation? 82 degrees, so it's, what is that? It's 355. So the temperature is 273.15 plus 82. Rumor has it that's 355.15, right? So again, if you want to do, this is not problem 36. Somebody's going to write this down. This is problem 36. We'll be like, huh? Okay. You can do it. The dominant paradigm is that we still use our little formula, right? Right, so the pressure is 1974.7 times some volume, pressure times some volume, right? And then N originally is 17.1 kilograms, right? T is, now we have to put the T in, right? Because the T is changing. So it started out 93 did it? Right, and then here it's less stuff, but it's more temperature, right? So it's like, the jury's out. We don't know which way it's going to go. Yeah? So whereas we decreased the amount of stuff, we also increased how fast they were going, which would tend to increase the pressure, right? Doesn't the V cancel? Right? Now, if you want to do it, and I said this last period, I thought this was a very ingenious thing. If you want to do it C to the envelope, this is great. I'm coming up with these all by myself, right? C to the envelope means a combination of C to the pants and back of the envelope. Yes? Isn't that good? That's nearly as good as rocket surgery, only it's not as good. So, if you want to do it C to the pants style, you're just going to go 1974.7. That is the pressure, and we're asking how the pressure changes, right? It's going to decrease because of the loss of stuff. It's going to increase because of the increase in temperature.
Can you explain that again?
C to the pants? Yeah, C to the pants. Okay, pressure. You have two different ratios of stuff, right? But decreasing the stuff is going to do what to pressure? It's going to make it less, isn't it? So I take that ratio, and I could do it 17.1 over 13.4, but I don't do that because I know it's less because of less stuff. So I make it less by that ratio, yeah? But temperature, if we increase the temperature, what does that normally do to pressure? Normally increases it, right? So I take that ratio and I flip it. You can flip it either way, right? But flip it the way you know it's got to be to make it bigger, right? This is easy with pressure. Pressure is like the one thing where you can go, okay, I can understand that in terms of everything else. Try doing it for temperature. Well, what is it? It's like more volume. Well, golly, then the temperature would have to be higher? If everything else stayed the same, right? If you had more volume, but everything else stayed the same, and volume. I know, it's hard, right? Yeah? You got to think through it. Do these work? Has somebody tried these? Do they get the answers?
No.
Do they get those answers? Has somebody tried these numbers? Yeah, and they get the right answers? Okay.
Yeah.
What?
Do we have to do your prior?
No, you never. You don't have to do. I don't need to corrupt you to my ways. Yeah, if you don't understand that and you like the PV over NT, that's great. I'm just, a third of you are so talented and gifted that I have to get like a special license to even like teach you. No, not really. But
No, yeah, I got you.